So, welcome back. We've just talked about the total differential in the last video, and now we're going to see a few examples for total differentials. So, we will start with a very simple function. We're just going to see the most simple multivariate linear function, and that is just taking a scalar product of a fixed vector and the input vector. So let A be a vector in R to the n, and we will consider the function f from Rn to R, defined as f of x equals A transposed x. So just the sum of the ai xi from 1 to n. We've already seen that example. We know already that the gradient of that function is simply 8 for every possible point. So the question is, what is the total differential? And can we find a relation to that gradient possibly? So let's have a look at that. Okay, so for some point x star in x, we need to find g such that this function f of x, that's atx, this is approximated by atx star, right? So this is the function at x star, plus we'd like to have some g transposed x minus x star, plus some error term. And well, atx is the same thing as atx star. Well, not quite. So to correct for that, what we can do is add atx and subtract atx star. And then we're exactly back at atx. Yeah, so the error we make is 0 with this approximation. So what we get here is g may just be set to a, and the error that we make is then 0. Okay, so what we get is g can be set to a, so f prime of x star is actually a for every possible x star. And that means in this case, we even get f prime of x is the same as the gradient of f at x. And our error function is 0. And that's not very surprising, because obviously this is a linear function. So if we find a linear approximation to a linear function, the best we can do is the function itself. And of course, in that case, the error is 0. That's just what happens here. Okay? So this shouldn't come as a big surprise. The derivative of a linear function is basically just the vector defining that linear function. Okay, let's have a look at a little more complicated example as well. If linear functions are easy, the next complicated thing we could do is a quadratic function. And we've also looked at quadratic functions in the context of partial derivatives already. So let's see how that works here. We'll take a matrix, an n by n matrix, A. To make things a little more convenient, let's say this is a symmetric matrix. And again, we'll take a point x star in R to the n. When we consider a function defined on R to the n, mapping to R, defined by f of x equals x transposed AX. Okay, so if you want a generalized scalar product, at least for certain matrices. Now, to make the notation a little more convenient, we'll introduce H, and that's just a shorthand for X minus X star, so that I don't have to write this all the time, okay? So in particular, X is then X star plus H. Okay, so with this, f of x is just x transpose ax, and we want to express that in terms of x star somehow. We want to say that is a linear term defined in x star plus some error, and we just need to find out what this error is and how it behaves. So we can replace x by x star plus h, and we get this expression here. And if we multiply that out, then what we get is x star transposed a x star plus x star transposed a h plus h transposed a x star plus h transposed a h. Okay, now we can see that in this expression here, that is the same thing as a x star transposed h, right? Basically, this is a scalar product of ax star and h, and the order of the factors in the scalar product doesn't matter, that's symmetric. Okay, similar thing here in the factor before that. That is the same thing as a transposed x star transposed h, just using the rules of matrix transposition here. And as A is symmetric, that's equal to a x star transposed h. So these two middle factors are actually the same, and that means we can write this whole thing as x star transposed ax star plus 2 times ax star transposed times h plus h transposed ah. And now remember, h is x minus x star. So what we have here is the first term, that's exactly f of x star. This term here. That second term, we'll say this here. This first part we call this g. And then h is x minus x star. And that leaves us with that last part here. H transposed AH. Well, this is then our error function evaluated at h if we define R of h as h transposed AH. Okay, so hypothesis is our g is 2 times a times x star. And our error function would then look like this, h transposed AH. So the question is, will that do? And to find out, we'll have to investigate the limit of R of h over the norm of h as h approaches the origin. Remember, h is the difference of x and x star, so x minus x star, and as x approaches x star, that's the same thing as saying h approaches the origin. Okay, so what can we do about this? Well, let's first insert our function here. So R of h is the function h transposed a h. And now remember, what we have here is actually a scalar product of h and ah, these two factors. And for a scalar product, there is a relation known as the Cauchy-Schwarz inequality. And what does that Cauchy-Schwarz inequality state again? Well, it states that basically a scalar product is bounded by the norms of its factors. So that's less or equal to the norm of the first factor h, or h transposed, times the norm of that second factor, ah. Okay, so that is due to the Cauchy-Schwarz inequality. Let's state that once more. Cauchy-Schwarz inequality says the scalar product of two vectors x and y, or even the absolute value, is less or equal to the norm of x times the norm of y. Okay, so we could even make absolute values around this here and this here. And this won't matter because the limit will be 0 anyway. Okay, so this we get by applying Cauchy-Schwarz inequality, and then the norm of h, which is cancel out. And that means what we get is the limit as h goes to 0 of the norm of ah. And now whatever a is, as h tends to 0, ah will tend to 0 as well. And that means the norm will tend to 0. So what we get is exactly what we wanted. This remainder, this error term r, goes to 0 faster than h. The difference of x and x star goes to 0. So what we get here is the differential of f at x star, or f prime of x star, is precisely that term that we had up here, 2ax star. And again, you might remember that we talked about the gradient of that expression as well. We did this in a more general setting without using a symmetric matrix necessarily, but if you do this with a symmetric matrix as a special case, then you will find that the outcome is precisely the same. Again, we get just the gradient here as a result. Okay, so that concludes our examples for total differentiability for now. In the next week, we'll be concerned with seeing connections between partial derivatives and total differentials. And we'll also hopefully have a look at optimization of functions using this new notion of total differentiability. I'll see you then.